Okay, we'll get started. As many of you know, there is an exam scheduled for Saturday, the 27th. Um, so great, happy weekend. You can take it anytime from the 12:01 Saturday morning till 11:59 Saturday night, 3-hour time limit. If you have formal accommodations through the UAC and I have your letter, then I will automatically build those accommodations in and you won't need to make any other special request. If you don't have formal accommodations, but you feel like your situation justifies some kind of flexibility in terms of test date or time limit, you can contact me via email and we can work something out. I realize anytime I schedule something out of class, I have to be flexible with people's schedules, understand some of your work or maybe traveling. Just let me know via email and we can work something out. The exam will cover substitution and elimination chemistry for chapter 7 and 8. Exam 2 only went up through substitution, SN1 and E1, but I'm sorry, SN2 and E2, but on this, I'm getting everything backwards. Sorry, I think on exam 2 you did SN1 and SN2. For this exam, you'll be doing SN2, E2, SN1, E1 all together and predict products, draw mechanism. It will also include, of course, chapters 9 and 10. Chapter 11 is, we're not going to spend much time in there. It's not really new reactions. It's using the same reactions in chapter 10, only using alkynes instead of alkenes. We'll do a little bit there, but not a lot. And chapter 12 won't be on the exam. So I anticipate finishing today and or a little bit Wednesday on the material that will be on the exam. All right, I think that's all the exam issues I need to address. Go ahead. Practice exam 3 does contain the problems on practice exam 2 that I told you didn't have to worry about for exam 2. Yeah. And that is posted on the content page of Learning Suite now, along with the key. Other questions? Okay, so today's topic is going to be on terpene chemistry. What are terpenes? They are natural products that have some key structural features and are all derived from the same simple starting materials, using chemistry that you know how to do from chapters 9 and 10. So the cool thing about today is you're going to be learning about how nature makes essential oils. We will not talk about their purported medicinal properties. As I said, the placebo effect is real, just don't pay a lot for it. And doubt anybody claiming any particular health claim that is not derived from randomized, controlled, double-blind clinical trials. That being said, you might be interested in how biology makes some of these molecules, and it all involves reactions that you already know how to do. The downside is none of this material is in your text, which I know you will create some anxiety for some of you. Everything you need to know we'll talk about in class, and we'll talk about the specific things I expect you to do based on what we've learned. Try to focus on the general application of principles you've learned previously, and try not to get lost in the details. So here we go. Let me show you some terpene natural products just to begin with. All of the steroids I showed you last week are derived from terpene natural products. I think I've shown you this one before. This one is called limonene. It is from citrus oil. It has the characteristic smell of citrus. You've seen another before. This one is linear and a little simpler. This one is called geraniol, which is in rose oil. There's a couple of more complicated ones. which you might hate, and that's okay. This one is called alpha pinene. And yes, that is a 6-membered ring fused to a 4-membered ring where the rings share 2 sides. It's like horrific. And then this is an isomer, a regioisomer called beta pinene. These are both hydrocarbon components of pine oil. And if you've used turpentine, these are among the molecules that are in turpentine. They're hydrocarbons and they dissolve oil-based paints really easy because they're really non-polar. There are others that I could draw. Let's see, draw one of them because I think it looks like a deck, which is kind of weird. But the cool thing is you get all this structural diversity, all these crazy shapes from the same simple starting materials using only a small alphabet of reactions. So yes, here is the duck molecule. It is called alpha thugine. And I think it's a component of like rosemary oil or something like that. If you're having trouble seeing the duck. Right? Hey, man. Got any grapes? I don't know how old that is. Were you guys in grade school or something? Probably. Yeah, go ahead. Yep, totally. So let's talk about what defines a terpene. Let's count carbons in these products. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Geraniol also has 10 carbons. If you counted for alpha pinene or beta pinene, there's 10 carbons. And also in alpha thugine, there are 10 carbons. I told you cholesterol was a terpene too. It has 30 carbons. And so the number of carbons has to do with whether or not we call these terpenes. There's a key subunit that is present in all terpenes. I'm going to draw a simple alkene. This alkene is called isoprene, and it has 5 carbons. For convenience, I know I'm not numbering it correctly for IUPAC, but I don't care. The isoprene has 5 carbons, a linear 4-carbon chain with a branching methyl group on carbon 2. And we'll call that an isoprene unit. And if you look at all of these natural products, they have, that I've drawn here, they have 2 isoprene units in them. Here is 1, 2, 3, 4, 5. And here is another 1, 2, 3, 4, 5. A molecule that has 2 isoprene units is called a monoterpene. I don't know why. If you have 3 isoprene units, you're a sesquiterpene, where the prefix sesqua stands for 1.5. If you have 4 isoprene units, you're a diterpene. I don't know why, but yes, if you have 2 isoprene units, that's what makes, at least 2 isoprene units or more, that's what makes a terpene. Does that sort of vaguely answer? Okay. In geraniol, you can see the isoprene units 1, 2, 3, 4, 5, and then another 1, 2. Oops, I didn't want yellow. I wanted orange. I actually wanted blue. Sorry. And we could similarly identify units in some of these other structures, so that is a bit more challenging. The isoprene subunit has some what I call directionality because it's not symmetric. You got the methyl group sort of on one side. And so I'm going to call the the end of the molecule that has the branching methyl group, the head, and the molecule that doesn't, I'm going to call the tail. And you can see that in geraniol, the head of the blue subunit is connected to the tail of the previous subunit. Another way of saying this is orange carbon 5 from the first isoprene subunit is bonded to blue carbon 1 in the second subunit. And in all terpene products, you're going to see bonds between carbon 5 of one subunit and carbon 1 of the next subunit. So in limonene, if we were to number carbons, we might say, well, let's see, 1, 2, 3 branching methyl group, 4 and 5. Here's the bond between 5 and 1 of the next subunit. And so that bond here between orange 5 and blue 1 in limonene is in the same place as the bond between orange 5 and blue 1 in geraniol. And we could make similar conclusions in some of these other natural products. So one skill to get from this section is the ability to recognize isoprene units in interesting and strange and complicated natural products. So let's try the duck molecule and see what we can do. I'm going to erase all of the shading. When looking, so the question might be identify the isoprene units in this natural product. So the first place you start is you look for the branching methyl groups. Why? Because if you can identify the branching methyl group, you already know what carbons 2 and 3 were. All right. So I've got a branching methyl group here, and I have another there. Another thing you want to do related to the branching methyl groups is you want to look for two methyl groups attached to the same carbon. Because if you look at the linear molecule that actually is a precursor to some of the more complicated ones, the head of the molecule always has two methyl groups on it, and the tail doesn't have any. So having identified those branching methyl groups, I know that the methyl groups I'm going to call 3, and then the tertiary carbon that it's attached to, I'm going to call 2. And then I'm probably going to say that this end of the molecule is the head of the linear precursor, though I'm not sure where the tail is. All right, are you with me so far on finding the branching methyl groups? Go ahead. Why isn't the double bond there? You'll see when we identify, and that's the second point is ignore pi bonds. Because you're right, the double bond went somewhere. We actually used it to make some of these other bonds to make the rings. And we'll talk about that later. But in identifying isoprene units, you're going to ignore pi bonds and also oxygens. And then there was one more step. Oh, and then we're going to look for the bond between carbon 5 of one subunit and carbon 1 of the other subunit. Okay, And this can help us figure out where the subunits are. So 1, 2, 3, then this could be carbon, this carbon here would sort of have to be carbon 4, but then I would need to figure out where carbon 5 is. And I've got a few different choices because carbon 4 is bonded to 3 different carbons. But whichever thing I choose for carbon 5, it needs to be bonded to carbon 1 of the next subunit. And it may not be obvious at this stage which place you should go. The one place you couldn't go would be right here. This can't be carbon 5 because carbon 5 isn't bonded to carbon 2 in the linear precursor. It's just 5 bonded to 1. So I'll give you a hint and say this is carbon 5, and that's our first isoprene subunit. That would make this carbon 1 of the next one, and this is the bond between the two. And then the remaining carbons, 1, 2, 3, 4, and 5 are there. Once you identify these subunits, you can get an idea of which bonds were in the linear precursor. And I'm sorry because I didn't say this, but all of these terpenes come from the same pathway. And that pathway branches out in other directions. This linear precursor, geraniol, can be used to make all of these other more complicated products. And so it's useful to try to distinguish bonds that were in the linear precursor from bonds that you had to form later, because that can help you propose how the molecule was made. And as I look at this, I see that the bond between 5 and 1 was in the linear precursor, but these other bonds between blue 4 and orange 4, and between blue 5 and orange 4, those weren't in the linear precursor, so I had to make them somehow through chemistry. All right. Similarly, we could look at alpha pinene. You see branching methyl groups there. That's probably the the head of our isoprene molecule. 1, 2, 3, 4, and 5. Here is the bond between 5 and 1, and here is 1, 2, 3, 4, and 5. So you can see that we had to make this bond between orange 2 and blue 4, and between orange 4 and blue 5. Okay, questions you want to ask there? I know we went through that kind of quick. Go ahead. For the duck molecule, how did I find the head? I looked for the carbon that's bonded to 2 methyl groups. And from there, I count 1, 2, 3, 4, and then 5. Sorry, maybe I'm not getting your question. Try again. Okay, yeah, you're looking for to identify the head of the molecule, of the part of the molecule that corresponds to the head of the linear precursor. You're looking for a tertiary carbon bonded to 2 methyl groups. And then that tertiary carbon is carbon 2, and the methyl groups are 1 and 3. And then the other carbons follow. How did I know that this portion of the molecule comes from this head of the linear precursor? Because that's a great question. I'm pausing. And that's a tough question because there are some cases where carbocation rearrangements happen and methyl groups move around. But most commonly, if you see a carbon in the product that has 2 methyl groups attached, it almost always comes from that head end of the terpene, or the linear precursor. Sorry, go ahead.
How do we identify the carbon 5 of the yellow isoprene unit isn't where the carbon is.
Right, great question. How did we identify that this now orange carbon 5 wasn't in fact blue carbon 5 and vice versa? And you wouldn't necessarily have known that. And you probably could have drawn a reasonable mechanism that would have been based on this carbon here being orange 5 and this being blue 5. I chose that because I think that reflects what is currently known about where that molecule comes from. I obviously can't penalize you for reasonable alternatives. When I've asked questions on an exam before, I've often highlighted the isoprene units for you and then said, of these bonds that I've highlighted between the isoprene units, which were in the linear precursor or which were not in the linear precursor. And so then, okay, either way, however you assign it, 2 of those 3 would not have been in the linear precursor. What else? Where, Sierra from the chat asks, where can we find problems to practice this if it isn't in our books? Practice the stuff I'm showing you in class, I guess. I can also reveal a few previous questions that I've asked on this subject, though I hate to do that because that means I can't use them on the exam and I have to write new exam questions, but for you, I will do it. I know you have no sympathy because you have to take the exam, so cry me a river, Dr. Price, having to write the exam. Well. All right. So let's now talk about the chemistry that these molecules can do. And it's straight out of chapter 9 and chapter 10, and actually 7 and 8. So the first one is leaving group leaves. Okay, so we'll start with the simplest isoprene unit. This is a molecule that is made in what's called the mevalonate pathway in biochemistry. If you or people you know are on statin drugs, I am, to limit familial high cholesterol, it inhibits the synthesis of this molecule. This is called dimethyl allyl pyrophosphate, which people abbreviate like this. I've abbreviated the pyrophosphate group. Basically, it's 2 phosphate groups linked together through a phosphoanhydride bond. It's a very good leaving group. It's the conjugate base of a strong acid, and 2 of those negative charges are usually chelated with a magnesium ion. So you're going to think of this as just a good leaving group. And with that knowledge that that's a good leaving group, notice that the good leaving group, you might think, oh, it's on a primary carbon, so why am I saying the leaving group can leave? But that's not just any old primary carbon. That's an allyl carbon. Allyl leaving groups can leave SN1 style because the carbocations they leave behind are not primary carbocations per se. They are instead resonance stabilized allyl cations. Notice that I should be able to draw a resonance structure where the positive charge is delocalized between carbons 2 and 5. Look familiar? And if you were to think about that allyl pi system, you know, you could remember we talked about molecular orbitals and how the LUMO is probably something that looks like this, where this is carbon 2, this is carbon 4, and that's carbon 5. The LUMO's on carbons 2 and 5, but never on the one in the middle. So terpenes do this kind of chemistry all the time to create a reactive intermediate and electrophile, a carbocation that can be attacked by other nucleophiles. Okay, so questions about leaving group leaves so far? I think you've seen something like this before, only the leaving group was chloride or bromide or something, but it's really no different. It's just the pyrophosphate group leaves. Okay. Second is nucleophile. Let's see, a pi bond, a carbon-carbon pi orbital acts as a nucleophile and attacks a carbocation. So let me show you an example of this. There is another isoprene unit precursor to all of these terpenes that we've been talking about. The one I've showed you is dimethyl allyl pyrophosphate. I'm going to show you the carbocation that we made from that dimethyl allyl pyrophosphate. And then the other precursor is an isomer of dimethyl allyl pyrophosphate. It's isopentenyl pyrophosphate, or IP. You don't need to memorize that name. It looks very much like dimethyl allyl pyrophosphate, only the pi bond is between carbons 1 and 2 instead of between 2 and 4. And this allows us to make the bond between orange 5 and blue 1 that is present in geraniol and all of those other terpenes we talked about. So here is a carbocation, resonance stabilized. The pi bond is going to attack the allyl cation at carbon 5. Why doesn't it attack at carbon 2? I suppose it could. There might be cases when that happens, but that's not how we generate that linear geraniol that I was talking about. Okay, so let's use our chemical intuition here to talk about what the products should be. Here is my orange isoprene subunit. Here is carbon 5, and we've just made a new bond between carbon 5 and one of the carbons of the blue subunit. Now there were two carbons involved in the pi bond, carbons 1 and 2. Which one gets the new sigma bond and which one gets the positive charge? Go ahead. Okay, you want 1 to have the sigma bond and 2 to have the positive charge. Why is that better than the alternative where 2 gets the sigma bond and 1 gets the positive charge? Yeah. Yeah, exactly. This, having the positive charge on 2 puts it in a more substituted position where it's more stable. This is an example of what you learned in chapter 10, Markov-Nikov regioselectivity. That is a preference when a pi bond acts as a nucleophile to form the new sigma bond with the less substituted carbons so that the positive charge can be on the more substituted carbon where it's more stable because of hyperconjugation. Okay? So in a lot of ways, though the players are unfamiliar, that is a classic chapter 10 reaction. All right, questions about making that new sigma bond? I'll point out this is, well, anyway, sorry, comment withdrawn. It was wrong. I'm going to say something wrong, so I'll stop myself. Okay. Now, this kind of thing can be used not only to connect these two individual isoprene units, but it can be used to make other bonds. So I'm going to show you another carbocation. And I won't show you right now where this carbocation comes from. But hopefully you'll recognize it as a familiar situation. Here is one isoprene unit, and here is another. We can number the atoms here, 4 and 5. And then here, 1, 2, 3, 4, and 5. This is still, it looks like, it's not quite this molecule, but it looks like the linear precursor. We still have that bond between 5 and 1. But now look, you've got a positive charge on carbon 5. It's resonance stabilized, but that positive charge on 5 is pretty close to the pi bond between orange 2 and 4. So again, you can have pi bond act as nucleophile. And we're going to selectively form the new bond between orange 4 and blue 5 so that in our product, the positive charge can be on the more substituted tertiary carbon. And I'll try to shade things to make everything consistent. In red is the bond that we had in the linear precursor. And then I'll use a different color for the new bond we just made between orange 4 and blue 5. Maybe we'll use purple. Okay, second example of pi electrons attack a positive charge. I've noticed students tend to get worried anytime we start making or looking at molecules with 5-membered rings or 6-membered rings. There's just some sort of, oh brother, I don't know what to do with that kind of thing that happens. And so you need to take a deep breath in these circumstances and pay attention to what you can ignore versus what you should pay attention to. Sorry, that didn't make sense. There are details here that you need to pay attention to, and other parts of the molecule you can ignore. When I see the pi bond here and the positive charge there, I can forget about the other carbons because I know this reaction is going to involve the pi bond and the positive charge. So I would focus on pi electrons attack the positive charge to make a new sigma bond here, and the positive charge ends up on the more substituted carbon. Once you've done that, you can worry about the fact that you just made a ring. Yeah. This wasn't the next step of that last intermediate. No, but we can get from here to here through a few other steps. Okay, other questions? Yeah. Would it ever use, say, this one? And the answer is no, because actually that pi bond is involved with in resonance with this positive charge, so they're not actually separate things. Yeah. Okay. So this leads us to a third type of reaction that can occur, and I'm going to fill it in here because it's part of the way we connect from the molecule we just made above with the 2 isoprene units to the more complicated one below where we made a 6-membered ring. And this is E1 style elimination of beta protons. So looking here on our carbocation, and maybe it will help to number the atoms. I'm noticing that there are a few different protons that are beta to the positive charge. You've got protons that are on carbon 4. If we eliminated there, you'd have a pi bond between 2 and 4. If we eliminated from carbon 3, you'd have a pi bond between 2 and 3. And if we eliminated from carbon 1, you'd have a pi bond between 2 and 1. Of those three options, one is clearly less favorable. Which one is that? And this goes back to chapter 7 and 8, where you learned about which types of alkenes are more favorable than others. So the one involving 3 should be the least favorable one, because that would give you a di-substituted alkene. Whereas if you eliminate from 4, you get tri, and if you eliminate it from 1, you get tri as well. Turns out that elimination from 4 is preferred, and elimination from 1 probably happens, but that product is not necessarily a useful precursor to anything else. Biology uses lots of equilibria where multiple things can form, and only the useful products get shunted off in other directions. A base, and we don't care what it is, it's probably either water or a basic group from an enzyme, removes that beta proton, and we form a new pi bond between 2 and 4 to give us the molecule that we're drawing here. And I will number atoms again: 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. There's a chemical strategy reason why you'd want to have the pi bond between 2 and 4 instead of between 1 and 2. And that's because once you put the pi bond between 2 and 4, your pyrophosphate leaving group is now on an allyl carbon. And you can do, remember step 1 that we talked about, example reaction 1 was leaving group leaves to give you a resonance stabilized carbocation. And only if you make the bond between 2 and 4 do you set up that same situation again. This is called geranyl pyrophosphate. If you get that pyrophosphate leaving group to leave, and then you have water come in and attack carbon 5, you can get geraniol, that linear molecule that we talked about above. So, Curtis, I think your question is, how do we get from here to here? Okay. Great. How do we get from there to there? Okay, so you rotate around which sigma? Okay, so we could redraw geranyl pyrophosphate. Another way to draw it would be, let's put orange 1, 2, and 3 there. Here's 4, here's 5. Oops. Oh, sorry. All right, fine. Now what? Still got a good leaving group. So how do I get from here to there? All I've done is rotate around a sigma bond. These are the exact same molecule. Go ahead, Staten. Does an elimination reaction need to occur? Maybe if by elimination you mean does something need to leave, the answer is yes. So if I got a situation where something can leave, look at the pattern. Look for an allyl leaving group. That means a leaving group at a carbon adjacent to a pi bond. Yep, you've got that situation here. So leaving group leaves. There's a little bit of an issue with double bond geometry, but we're not going to belabor that point. Leaving group leaves to give you the carbocation. and then pi bond attacks, carbocation to give you the product shown here. All right, seeing how the dots are connecting? No. Curtis, are you worried about double bonds? We had the leaving group leave to give you a carbocation, and then this is pi electrons attack a carbocation to make a new bond. Yeah. Sure, go for it. So what actually happens here, notice that the problem is that carbon 5 is cis to carbon 3 and trans to carbon 1. But in the carbocation that makes the 6-membered ring, carbon 5 is cis to 1. And so you have to change that. What actually ends up happening is the leaving group leaves to give you this carbocation, which is resonance stabilized, and you could draw it like this. Oops, just drew the same thing, didn't I? You could draw it like this. At that stage, the pyrophosphate group, there's evidence that the pyrophosphate group comes back on. That gets rid of the resonance and allows this to be a sigma bond that you can rotate around. So you rotate to form this, then the leaving group leaves again, and then you've got a resonance stabilized carbocation. So it's a pretty quick process. Leaving group hops off, hops back on the other carbon, rotate around the bond, hops back off, and everything's in the appropriate place. I just like to skip over that because it doesn't make it can be confusing as to why is the leaving group coming on and off again. Well, because that gives you the desired geometry to get you the desired product. In terms of why any of this happens, it has to be because the synthesis of that natural product gives some selective advantage to the organism. Okay. So we've seen 3 different applications. We've seen leaving group leaves to give a carbocation that's resonance stabilized. We've seen pi bond attacks carbon, and we've seen then E1 style elimination of beta protons. The last thing that we'll talk about is, or the last fundamental reaction step is carbocation rearrangement. Okay, now I want to distinguish between what carbocation rearrangement we're going to do here versus what I've expected you to do before in predict product situations. Recall that when you're predicting rearrangement, I've told you to watch for secondary carbocations adjacent to tertiary or quaternary carbons. That's when I want you to be able to predict a rearrangement can occur. However, in biology, it's easy for other kinds of rearrangements to occur as well. Some of you have asked before whether I would expect you to predict that a tertiary carbocation could rearrange to become a different tertiary carbocation. And I've said before, don't worry about that and predict the products questions. But it's a legitimate possibility. Consider thermodynamically what we're talking about. Let's imagine a rearrangement that allows the proton on carbon 4 to lean over, passing through a bridged carbonium ion transition state or intermediate, and then finally to create a new bond between orange 2 and this proton, and the positive charge would end up on carbon 4. That rearrangement would be a 1-2 hydride shift, and it would take a tertiary carbocation and rearrange it into a different tertiary carbocation. In this case, one in which the positive charge is here. Here is the proton that used to be attached to carbon 4 and is now instead attached to carbon 2. I'm going to shade those subunits, and I'm going to continue making the bond lines as we've shown before. All right, that is a carbocation rearrangement that traded one tertiary carbocation from another. Now consider on an energy diagram what that would look like. You'd have a high energy tertiary carbocation intermediate, some transition state to another tertiary carbocation intermediate, about the same stability, equilibrium constant probably pretty close to 1. So that means this is reversible and both carbocations are accessible. How do you know which one you should form? Well, it depends on what product you're trying to get. How do you know what product you're trying to get? Well, I would show you that. So in a mechanism question based on this stuff, I might ask you, for example, where does alpha thugene come from? Or where does alpha pinene come from? In fact, let's actually do that. Let's look at the structure of thugene and let's see if you can tell which of these two carbocations would be a useful precursor to thugene. So I'm going to, again, number the atoms because that's going to help you see where bonds need to be made. Let's look in thugene. We already have in our carbocation over here the bond between 5 and 1. And we already have the bond between 4, orange 4 and blue 5. We actually have that in both of these carbocations. The bond that's missing is the one between blue 4 and orange 4. So of my two carbocations, A and B, which one do you think leads to alpha thugene and how? Based on these 4 reaction steps I've shown you, can you see where we would get that from? Go ahead, go ahead. From B, okay. Pi bond across the ring attacks the positive charge. That's going to make a bond between either blue 2 and blue 4 and orange 4. So which one should it be? Which, which 2 or 4, which gets the new sigma bond? 4. You know that because that's where we're trying to end up. But also you could predict it because that's what puts the positive charge on more substituted carbon 2. All right, so I guess I need a different color than purple now. No, can't use orange. Pink, that's lovely. Okay, there's the bond that we just made between orange 4 and blue 4. I'm sorry, I'm hurrying and then suddenly making all kinds of silly errors. 3, 4, 5. Okay. And yeah, making that bond from the carbocation B between 4 and 4 gives us that connectivity that we were looking for. And it also puts the positive charge on carbon 2. Now, how do I get from the carbocation C to my alpha thugene product? Elimination from which carbon? Okay, beta carbon 1, sure, have a base, remove a proton to create the new pi bond. Okay, so with just an alphabet of 4 different reactions, we're able to develop really crazy, complicated structures. And nature does this all the time, and the structures are inspiring and beautiful, and many of them have led to medicinally important compounds. Maybe an example I will show you is of a structure. One of the examples I'll maybe post on a supplement to the practice exam is of a structure called taxadiene. This is a terpene precursor to the drug Taxol, which is used for breast cancer. and it happens through this pathway. Anyway, we'll maybe say a few more words about this next time. We'll talk a bit about chapter 11, and we'll move on to chapter 12. See you Wednesday.